Well, good afternoon, everyone. My name is Steve Welch. I wanted to introduce myself first. I'm the National Sales Manager here at SolidCAM and would like to thank everybody for the time and the attendance. We're very excited to show you our patented and proprietary iMachining technology. So we'll get to that quickly. We're going to try to keep this to under a half hour, maybe closer even to 20 minutes. So hoping to make the best use of your time. Just a couple quick housekeeping items before we jump into the content. Everyone is on mute today just so we can keep the background noise down. You should have the appearance of a split screen on your computer. We're going to cover just some general information on SolidCAM and iMachining, and then you should be able to slide the screen down, and when we get to the live cut, enhance or enlarge that portion of the presentation. So there is a questions pane also in the flyout menu of GoToMeeting. If you do have any questions, feel free to hop into that and type any questions. We'll get to those kind of at the end of the presentation. So one other thing, as it goes with GoToMeeting, we want to make sure everybody can hear us. So if you could just type in quickly into either the chat or the questions pane, if you can hear us, that would be appreciated. So.
And if you can see the screens.
If you can see the screens, Ken, thank you. No, how that goes. You're never 100% sure. So if somebody, you could just type in if you can see and hear us, that would be appreciated. So.
And for those of you that are unfamiliar, we have a couple of coming in with an all good. In the GoToMeeting control panel, if you look down towards the bottom, you should see two drop-down areas where you got questions and chat. And if you just pop open either one of those and just type it in there and send it, all be great.
Perfect. Good deal. All right, I think we got that out of the way. Let me introduce the members of the team on the presentation today. The gentleman just speaking is Mr. Ken Merritt. He's a senior application engineer for us here at SolidCAM, along with helping manage our partner relationships. We also have Kevin Rankel on the call. He's, again, a senior application engineer team lead for us. Should have let you say hi, Ken. Go ahead and say hello, if you would.
Hello.
Perfect. It's about as formal as we get around here. And Kevin Rankel, are you on the line with us as well?
Yep, I'm here, guys, and just want to thank all you guys for attending today.
Yep. And then actually doing the live cut for us today is our friends and partner over at Levil. Ricardo and Andreas will be doing the actual live cut for us today. Ricardo, Andreas, you there?
Yeah, we're here. Hello, guys.
All right, beautiful. Good deal. Well, just a quick agenda of what we'd like to cover today. Like to really give you an in-depth look, and you'll see a live cut of our product called iMachining in action. This isn't a pre-recorded dog and pony show. This is actually going to be a live cut that will kick off shortly after we give you a little overview on the technology itself. So we'll describe the part to you. Our friends at Levil will describe the machine that they'll be running it on. And really an interesting thing here is that the Levil machine is a smaller desktop machine. So I always like to stress the fact that you don't have to have a super large, state-of-the-art, high-end CNC piece of equipment to get the benefits of iMachining. We feel we maximize the production of any machine that you would use iMachining with. So we'll describe the part, and then we're going to run that part live for you folks. And then Ken, at the end of the presentation, does have a science of cutting angle for those that might be interested in seeing a little bit behind the scenes what exactly makes iMachining work. So I'm going to just quickly kick it off with SolidCAM. It won't be a long commercial, I promise. We've been around since 1984, developing, selling, supporting CAM software. Our product integrates into SolidWorks, Autodesk Inventor, and iMachining is actually a plug-in for Siemens NX as well. Very strong, up to 5-axis simultaneous cutting, lathe, and live tooling capabilities to support the most complex live tooling machines on the market, and we're in the process of really rolling out the control for Swiss screw machines here in the U.S. Last thing on us is we handle customers here directly in the U.S. and Canada with the direct sales and support team. So no middleman or kind of filter between us and our customers here in the States and Canada. So, with that said, Ken, I'd like to, if I could, throw it over to you for a little bit about what we're going to show today.
Absolutely. Appreciate that. Well, thank you again, everybody. I'll kind of echo what Steve was saying. We really appreciate you being here today with us and joining us for this. Let me talk just a little bit about what we're doing. iMachining is a patented algorithm within our software that allows us to manage the way that the tool is engaged with the material in such a way that we can cut significantly more aggressively than you would think is even possible. And what we're going to be doing today is showing you on a small desktop machine how this works. But kind of a little bit about what iMachining is. iMachining takes into account the machine kinematics, the material properties, and the tool characteristics, and it kind of marries all those things together and gives you this machining level slider where you can choose what aggressiveness you want to run at, and that will automatically set your feeds and your speeds and your minimum and maximum cutting angles and so forth for each given material. So it kind of gives you a real quick way of doing it, and we like to kind of look at this little marker we got up here. It doesn't really matter how fast everything is. If you can't see what you're doing with it, if you don't know how to get there and how that relates to iMachining is, some of the other systems out there on the market, they make you put all the individual parameters in. They don't do any of the same stuff that we do, not quite as fast and as efficient as we do, but they also force you to put all the parameters in. So with iMachining, you kind of have some help with the iMachining wizard, and it gets you kind of a step up on the game, if you will. Now, today we're going to be cutting 1018 cold roll steel, and you can kind of see the size of the part and everything here. The tool is going to be a GW Schultz. It's a 3/16 inch 4-flute, and it's from their HGW series, what they call the Hura mills. Very, very cool tool. Nice coatings on it. Performs very well. We're also going to be running this on the Levil LMV 300 Quicksilver machine. This is a new machine in the market that Levil built specifically to our spec for a small machine to do high performance machining. Okay, and so I'll let the guys from Levil get into it a little bit here in just a moment and talk to you a little bit about this machine and availability and maybe even some pricing ballparks and so forth on it. But this is what we're going to be cutting on today, and it's what we also ran at IMTS here just a few months ago. So as we get into this, I do want to talk just a little bit about the holder that you're seeing in there, and that is the RegoFix Power Grip System. We're a big believer in holding on to the tool. Okay, we're going to be getting real aggressive with this cut, and when we do that, you want to kind of make sure you're holding on to it. I have found the RegoFix holders to be one of the best I've ever run into. I've got about a 30 plus year career in machining, and so far I haven't seen anything that beats the RegoFix. So something to think about, something to look at if you guys get a chance. It's a great opportunity to take a look at something that's pretty cool. At this point, Andres, you want to go ahead, or Ricardo, either one of you want to go ahead and just talk a little bit about your machine, and then let's fire this thing up and let's let them see how it runs.
All right. Hello everybody. My name is Andres. I am the general manager here at Levil Technology Corporation. So the machine that Ken has been talking to you was just released during the IMTS show. It is our newest version of a tabletop CNC milling machine. It is standing, the whole body is standing on a granite bed, making it very, very rigid, which allows for the high speeds that the SolidCAM software is making the machine do. So without further ado, let's just get the program running so you guys can see the fast cutting, and we'll take some questions at the end, I guess.
Okay, and I'll do a little bit of describing as we're watching the cut. So at this point, guys, everybody, there should be a bar between your screens, between the PowerPoint presentation and the camera inside the machine. If you would, you can slide that bar down just a little bit. Just grab on it. You'll see the double arrows pop up, and you can expand that area that is the video or the camera inside the machine. And then whenever you're ready, Andres, go ahead and fire it up, and I'll kind of describe what's going on.
Before we start real quick, guys, let's just do a friendly competition. I see we got a bunch of people here. Why don't you guys type in what you guys think the feed rate or the cycle time would be for this cut right here, and we can see how what you guys think, and then you guys can throw your guess in there and see who's the closest.
Perfect. Ken, can you describe the part again? I think it's a great idea.
Yeah. This part is actually, this part's actually a little smaller than these dimensions. This was another part. This one is 3.5 inches by 2 inches. So sorry, my bad. I've got bad numbers in here. We've done this on bigger machines as well. But this is 3.5 inches by 2 inches and by 1 inch thick. So you can kind of see it's a little tiny mold core, and we're going to machine this whole thing out to a near net, ready to run a finishing tool on. So if you could just go ahead and type in your thought processes, and thanks, Kevin. It's kind of fun to have a little friendly competition.
Mm-hmm. Amen.
Said we got a bunch of people in here, so we can see who gets the closest. I see we got a couple of guesses in there, but
cold rolled steel, Ken, right? And a 3/16. Yep.
1018 cold roll steel. It's a 3/16 inch diameter cutter, and we'll be going up to 3/8 of an inch depth of cut.
And roughing only, right?
Yeah, we're just roughing on this one. We're not going to be putting the finishes passes on it, but we're going to take it to a near net finish where it's ready for a ball tool to go on it.
Perfect.
Just let me know when.
Alrighty.
Guesses are in.
Yeah, let's go ahead and fire it up. And then, like I said, as it's running, I'll kind of describe what's happening.
All right, here we go.
All right, so we're going to helix into this. And again, we're just going to peel right down into it, 3/8 of an inch deep. And then the first thing that the system's going to do is what we consider our morphing spiral. As you can see, it took that area out very, very quickly. And then it's going to achieve a need to go into what we call D-slot tricoidal. And in the D-slot tricoidal, it repositions itself continuously as it nibbles away at the material. But again, you can see how quickly it is removing that material out of there. Okay, and we're running about 18,000 RPM, probably running in the neighborhood of 220 or thereabouts inches a minute maximum. And we're using a 40-degree cutting angle on this. And then, Andreas, if you could take a look over at the load meter, this machine runs about 23% load to run at 18,000 RPM in the air. What are we running right now in cut for a spindle load?
Right now, it is varying from about 30 to 45.
Okay, so we're in the neighborhood of a 7, well, that's about a 7 to 23% or 22% delta on that spindle load, and this is basically a 3.7 horsepower wood router spindle that you're seeing cut here.
Ken, what's our delta cut?
Right now we're at 375, 3/8 of an inch. That whole internal area of the goggle was at the same depth of cut. Now on this outside, you're going to see it starting as it begins to work its way in. It's going to start staircasing. What I want you to notice about this, though, iMachining is very, very optimized. Notice that it is regionalizing where it cuts. So it did that whole cut around that end, and now it's working on just the corner. It gets this corner into a state where it needs to blend it, and it is going to go then work on the other corner and bring it into the condition where it needs to blend between the two. And you'll see it kind of working back and forth like that. Notice also that it's not lifting up to the rapid clearance plane very often at all. And the reason we can do that is because the algorithm in iMachining, as it is running, is actually updating the remaining stock with each movement of the tool during calculation time. And so we always know where the stock is, and we can do what we call these detour repositioning moves, which allow us to move on level back to the next place where we can cut in a high G1 feed rate move. That keeps it very, very smooth. You'll notice you're not seeing the machine stop and start a lot. And that's because everything in the cut is a very tangent movement, and we're not going between G1 and G0. Okay, we're always staying in G1 and managing that cut appropriately. And so you can kind of see this thing very, very quickly removing the material around this and then working to a next region and bringing that region into a condition where it begins to blend with the other region. And you should also be able to hear this cut a little bit. You'll notice that the tone doesn't change much. And the reason that is because SolidCAM works with a variable cutting angle. We work between a minimum and maximum range. In this case, between 15 and 40 degrees. When it's ranging, it's also modulating the feed rate so that it's maintaining a constant chip thickness at the actual cutting angle. And so this is one of those things where the software does a very good job of making sure that the spindle load remains very, very constant. So you're not going to get shocked to your tool.
If I could throw out there, you guys will notice that we are not using coolant at all. All the heat is going out in the chip.
This shop air, we're not even using vortex cooling air or anything like that. This is just standard shop air blowing through the nozzles and basically just getting the chips out of the way. We don't want to run over chips. And you'll find it's going to be kind of interesting. You'll see it when this is done cutting. I'll ask Andreas to be careful, of course, but reach in and grab that tool when it stops spinning and show you that it's not hot. It doesn't heat the tool up when we do this. And it looks like we've lost the audio for some reason.
There
it is. Okay, so we're almost done with this. Again, I want you to remember this is a desktop CNC mill with a 3.7 horsepower wood router spindle.
I know it's hard to see this machine from a picture, guys, or even from the camera right now, but this thing would sit right on your workbench in your garage.
Yeah. Beautiful idea. All right, check that guy and make sure, but it shouldn't be hot.
Nope.
Yep. Room temperature?
Room temperature.
That's a beautiful thing.
Yep.
And you can see some beautiful gold chipped in there, so we know that we're not overheating anything. You'll also notice the consistency of those chips. They all look the same, and I'll tell you what, guys, you can actually take a pair of micrometers and start measuring these chips, and they'll be within a tenth or two of each other. It's amazing how consistent those chips are throughout this cut. So the idea behind iMachining from SolidCAM is that it takes advantage of information that you can give it about the material, about the machine, and about the tool, and then it can coordinate all that information into the proper cutting parameters to very, very effectively and efficiently remove material without creating stress or heat induction into the part or the tool or stressing out your machine. So tool life goes up, material removal rate goes up, and post-machining processing actually goes down because we're not inducing warpage into the part because we're not creating heat in it. Okay, so some really great ideas. At this point, let's go ahead and go back to the PowerPoint. So shift your screens back.
Do we have a cycle time to see who is the closest?
Well, I'm sure we do. Andreas, what you see for a cycle time on that? He might not be there now.
He might have dropped off.
He may have.
There you go. All right.
Yeah.
Can you hear me now?
I got you now.
Yeah. Okay. 5 minutes and 42 seconds.
5 minutes, 42 seconds. Remember, that's a 3.5 by 2 inch block. So that gives you kind of an idea. We took a lot of material out of that in 5 minutes and 42 seconds.
We'll just call Trevor C the winner chicken dinner.
Exactly. Yep. Ken, the other thing I was going to chime in with too is we really see good results in aluminum or harder materials, correct? And the harder the better, right?
It really works throughout all different grades of materials. There's so many benefits to the way iMachining cuts. Again, even in fracture critical materials like graphites and acrylics and things like that, iMachining can do a much better job because we're not applying a linear force to the material. So we're reducing the potential for fracturing or cracking it. All the way up through hard materials. Even up into ridiculously hard materials. We've got some pretty crazy stuff going on with fully hardened ceramics as well. And so iMachining can really benefit you throughout the full spectrum of what you're cutting.
Yep. Inconel's titaniums really shines, right, Ken? Yep.
Absolutely. Absolutely. All right, so let's go ahead and go back to the PowerPoint for a minute, and let me just kind of close this out here. I want to talk, Steve brought up something that's very important for you to understand, and that is that you don't have to have a super high performance machine in order to be able to achieve a winning combination with iMachining. Now, what we showed you today is a machine that has been designed, even though it's small, has been designed for high performance and high accuracy and high smoothness. But let me take you into an old beat-up machine. This is one of our customers up in Colorado. They're using a, believe it or not, this is a Haas TM2 open bed tool room machine. And this pocket over here, this is a mild steel. I don't know exactly what grade. It might have been a 1020 or 1040 or something like that. But he's using an OSG Exocarb 3/8 inch 3-flute end mill. And his way of cutting this on this machine has 4,500 RPM spindle. We could only get about 50 inches a minute out of it before we started running into hesitations and such from data saturation. But he was only able to cut this 50 thousandths deep per pass at 2,200 RPM and about 18 inches a minute. Now, that took him 2 hours, 26 minutes to cut this pocket. The bottom 50 thousandths of that tool was virtually destroyed by the time he got to the bottom. And so he was putting a new tool in to finish the walls and then using that new tool to cut the next pocket, the next part. So he was looking for something better than that. Now, this is not a sexy video. It's not real impressive, but there's something really cool about it that you need to see. I'm cutting at full depth. I'm using all 4,500 RPM of the spindle. And I'm using all 50 inches a minute that this machine will give us. I'm taking advantage of everything in this machine I can take an advantage of. But notice again, I'm at full depth of cut, 1 inch deep. All right. Now let me go ahead and move this forward a little bit so we don't spend a bunch of time just watching it cut slow. Okay. But notice what's happening here. At the end of this cut, notice the chip color is really looking good still. There's nothing wrong with this tool at all. Let me go ahead and take it up here towards the end where it really starts to shut down. Okay. We're done with this pocket. Look at the chip color in here. And that was 7 minutes and 26 seconds. So even though this isn't a high performance situation, look at what we gained. He was 2 hours, 26 minutes cycle time here and burnt the tool up by the time he got done roughing. We cut it in 7 minutes, 26 seconds, same pocket. This tool was virtually unaffected. We pulled it out, looked at it under a scope, and it looked brand new. We put it back in. We cut 3 more pockets on this bar just to test it out. And at the end of the 4th pocket, that tool still looked like a brand new tool. There's a little shine mark on the edge of the flute where the sharp edge had kind of abraded the coating back just a little bit. If you're familiar with Exocarb tools from OSG, they've got a corner chamfer instead of a corner round. Even the 2 corners of the corner chamfer were just barely starting to turn color. So could we have done 8 or 10 pockets? Possibly. 8 for sure. 10? Yeah, probably. He was getting 1 per tool. Okay, so tool life went up dramatically. Cycle time came down dramatically. Volume of material removed over time went up amazing on this. Okay, so it's kind of a thing I want you to think about is be aware that you don't necessarily have to have a super performance machine. iMachining is going to take whatever machine you're using and whatever tooling you're using and make it run better. Now, as you can see here, he's in a ER32 collet. Okay. Steve, did you have something you wanted to say?
No, I do.
No.
But before we move on here, one thing Ken, I think you forgot to mention is when he was doing that pocket the traditional way, that machine was vibrating and making noises that you would not want to hear.
Oh, yeah, absolutely.
So you're getting the longevity of your machine as well because we're taking that load off the spindle, and got all the chattering and all that stuff. So, sorry, I just want to throw that in there.
Yeah, great point. Good point, Kevin. Good point. Yeah, I forgot to mention that. It was a dramatic difference in sound of the machine. And you guys can hear it when you listen to a cut on any of our videos. Go up on YouTube, you can see all kinds of videos on this stuff. Now, there's a couple things I want you to be aware of. And so I want to kind of take you through this a little bit. You're not required to use super performance tool holders and things like that. But I want you to be aware of some things that can happen. Okay, this is an inferior performance tool holder. I'm not going to mention the name, but it's not one of the better ones on the market. But it's actually a milling chuck. This is not an ER32. Now, I was doing something a little beyond what you should be doing here. I'm testing a new tool in here. It's a 12 millimeter tool. It's a 7 flute tool, so there's an awful lot of torque on that. And it's a very, very high helix. It's a 50-degree helix tool. And I was doing some testing on this to see what this tool would put up with. And I want you to see something that happened that I had to catch real quick on this before we snap the tool. But you can kind of see this thing cut, and you can see it carving a lot of material. We're taking a 50-degree cutting angle here and just removing material ridiculously fast. Now, again, I'm not looking at something that's a production rate. So I'm not terribly worried about this holder not holding on to the tool properly. But just so you see this and are aware of it. This is running at 12,000 RPM, 350 inches a minute at 50 degrees cutting angle at 800 thousandths depth of cut. Now I want you to see something here. Missed it. Hang on a second. Let me bring it back. Try that one more time. All right, we'll try to catch it on the next lap. See that right there? This tool is actually being sucked out of the tool holder. Now remember the numbers here. We're at 12,000 RPM. This is a 12 millimeter tool, 7 flutes, 50-degree helix, 50 degrees cutting angle at 800 deep. That's an awful lot of torsional force on that tool. Okay, so pulling it out of here at that rate, not really surprised. It's a milling chuck, okay? But this is where I want you to see something that's really kind of cool. The RigoFix holders actually give us phenomenal performance. Now, I took that same tool after that cut, pulled it out, took it over to a different machine, put it in the RigoFix. Now I'm running it at 14,000 RPM at 512 inches a minute at the same 800 depth of cut and 50-degree cutting angle. And this thing cuts the entire part and never even begins to move that tool. Okay? Now, the point being here, look, if you're going to get seriously, and I mean seriously aggressive with iMachining, you need to hold on to the tool. If you're going to run in the more moderate range, you can actually get away with ER32s. We've even run with ER25s and ER20s. But you do want to make sure you're not trying to overdrive it. Okay? Because if it doesn't hold on enough, if the tool spins or the tool pulls out, it will break the tool, of course. And so there's things to pay attention to and things to be aware of. iMachining can run at any level. And this is what's really great about iMachining. If you have to run in an inferior holding condition, just bring your machining level down to 4, for instance. Okay? And iMachining will run significantly less aggressive and therefore provide a good clean cut even with an inferior holding situation. That's the reason that we put that machining level in there.
Hey, Ken.
Yes.
Stop you real quick here. We have a question from one of the attendees, and he's wondering, does the wizard tell you the max depth of cut? Do you have to tell the wizard exactly what end mill you are using, flute, angle, helix? You want to explain that?
Okay. You betcha. I'll go into that. What it does like I said, it takes into account the tooling characteristics. So you're going to tell it what grade of carbide it is. You're going to tell it what the helical angle is on it, what the cutting depth is on the flutes, and so forth. And then iMachining is going to manage all of that based on some settings that are internal that tell it, what pi section it's allowed to use at what depth before it begins to overstress the spindle and potentially stall the spindle. So iMachining will automatically adjust some of those depths for you. Now, if you force the depth, iMachining will typically drop the cutting angle. And so it balances those things out. If you know that you can handle it, you've done it before, or you worked your way up to it, there's also the ability to override the settings from the wizard. And so once you learn how to use iMachining, it's really very effective. The automatic stuff that it does is going to err towards the conservative side, if you want to look at it that way. But if you are very comfortable with the way it's running, then we can show you how to override those parameters and get a little bit more aggressive with it. Okay. Now, notice this is a 5x3 plate of steel, and we went 800 thousandths deep, removed all that material in 1 minute, 27 seconds. Again, nothing like what I would consider using for production rates. But I was trying to test this tool. I was actually trying to push this tool to its breaking point and find out what it would actually do. And this is the second part that I ran on that tool, and it's still sitting here at my desk. It's dead sharp. So I haven't found its limit yet.
Nice.
All right, so just a little bit of thought process on that. If you have questions about SolidCAM, you have more questions about iMachining, feel free to contact us. Go up to our website, take a look at things. There's all kinds of stuff up here on the website. You can look at iMachining videos. You can see SolidCAM professor videos up here. You can get access to Kevin's KevCAM class, which is a night school that we make available to you every week. There's all kinds of resources available to you to do a little bit more investigation and find out how much you really like about this stuff and get your answers.
Good deal, Ken. Maybe throw it out for any other questions. Please, everyone, keep in mind, too, if you'd like to see a little bit more behind the curtain about the science of iMachining and what makes it tick, I think, Ken, you are planning on doing a little science of cutting angle presentation?
Yes. Yeah, I plan on going into that next, but what we wanted to do is get you through this part of it first, let you see the cut, let you kind of get a brief idea of what it's all about, and then if you can stick around, please, I'm going to go through the science of cutting angle, probably take me another 25 minutes to go through that, and then that'll be the end of it completely. But we do realize that some people have to get back to work, so we wanted to make the front end of it, kind of short.
Yep, perfect. Yeah, and again, if there are any questions, feel free to type those in. While those are coming in, I'll quickly thank everybody again for the time. We definitely appreciate it. Hope you found it valuable. If you would like more information, we're at solidcam.com, or you can contact us directly at 866-975-1115. We cover the entire U.S. and the entire country of Canada, so would love to. If you'd like more information, engage with you further, even kind of focus on your own parts in a private one-on-one overview as well. So,
and just for those of you who wanted to take a look at this, this is kind of just an overview of how the system works, the dialogue. You set your geometry in here, you choose a tool from our tool tables, set your levels, go into the technology wizard, and you can set your level of cut here. This is just a slider for very conservative to very aggressive. Okay, you can see this in two views. View one shows you spindle speed, feed rate, and step overs, radial engagements that a lot of people are used to looking at. View two is what I like more. This shows our the cutting edge velocity, the actual chip thickness at the cutting edge, at the cutting angle, and then what our minimum and maximum cutting angles are. And I prefer this view, but that's just kind of a personal thing. You also have the cutting conditions here, like I was talking about. You can override stuff if you want to. And then, of course, your technology page gives you your wall offsets, scallop heights, and stuff like that for handling these staircasing issues here. So pretty simple to work with. Like Steve said, we'd be more than happy to take you in a deeper tour of it if you have an opportunity to. At any time, just give us a call and we'll connect up with you.
Looks like that's it for questions, Ken. Not seeing anything else coming up. So
okay, cool. Alrighty, well, let me go ahead then and step forward into the science of cutting angle, and we'll get a little bit deeper into the technology of what's actually going on here. I like to think of this as kind of digging into the physics, if you will. But the idea behind the science of cutting angle is how we're managing the tool material engagement. Okay, now we're not really cutting steel or metal, right? We're actually more chiseling it. This is a great video to show that. This is a very, very high-speed video taken at highly magnified level. This is a lathe insert that is cutting through 1018 cold roll steel. And you can kind of see here by looking at this. This is I believe, a 1/1000th or 1.5 nose radius here. So you can kind of tell how big the chip is. Looks like it's about a 6 to 8 thousandths chip thickness. But this is a great thing to look at. Look at the material kind of bending underneath here and then returning up to this line here. What that is elastic deformation, okay? But what's going on along this line over here, this is known as plastic deformation. This is more of a chiseling effect. This is how the chip is curled up, okay? And so by looking at this interface here and understanding the dynamics behind this plastic deformation and what occurs with that, we get a much better understanding of chip removal and what we can or can't get away with the performance of the tool. Now, one of the things that is highly critical in this is the cutting edge velocity relationship with the chip thickness. Okay. If these two get out of balance, we got problems. And so that's what we want to kind of teach and help you understand how to work with that. Think about the tool material interface. You've got a rotational velocity on the cutting edge, right? You've also got a forward velocity on the movement of the tool and its feed rate. And that's relative to the quadrant of the tool, to the direction that it's traveling. When the cutting angle is in balance with the rotational feed rate, or the rotational velocity, excuse me, the pressure vector on the flute is very near tangent to the actual curve of the flute as it is in the material. Okay, now that's critical because think about carbide. Carbide is a very, very hard substrate, right? And yet carbide is also brittle. It doesn't have really good tensile strength, if you will. The ultimate tensile strength of carbide is actually pretty weak, but it has fantastic compressive strength. So if we can keep this pressure vector on the end of that flute in a compressive form or a compressive direction, then this flute is going to last a whole lot longer. If we are putting a tensile force on this tool, on this flute, then it's going to microchip much sooner and wear out and go away. Okay? And so we want to kind of balance all these factors out. But as we look at the cutting edge velocity, I want you to think about something. If you take a really sharp knife and just push straight down on a tomato, it'll chop the tomato, but it's going to squish it on the way down, right? But if you take that same sharp knife and you drag it very fast across the tomato, it'll virtually slice through that tomato without impacting it in any way, shape, or form. And that kind of illustrates what I'm talking about with the cutting edge velocity. What happens is as we get an increase in the cutting edge velocity, we actually get a decrease in the latent energy of plastic deformation. That's what allows us to carry a bigger chip, which can handle more heat. And so there's a cyclic balance that goes on between the heat generated by the velocity of the cut and the heat dissipating characteristics of the thickness of the chip. And so when all of that is balanced in together, this works very, very effective. We also want to make sure we have pressure vector stability, because one of the things that we have always had problems with on machining centers is harmonic vibration, right? Well, we want to get rid of that, and I'm going to show you how iMachining does that. The flute integrity is very, very impacted by the stability of the pressure vector. If this force vector is stable in a compressive direction, then the flute will last much, much longer. Okay? So let's look at a conventional or traditional style of cut, right? Because of all these sharp angles of change, we're in, typical offset toolpath pattern that we've always seen for pocketing over the years. Each one of these changes of direction become what I like to call a compression zone in the cut. At that point, the tool goes into a full slot width cutting mechanism because it's completely enveloped into it before it starts out this direction here. Traveling along this cut to get into the step over, I'm suddenly overloading the tool as it drives in here, okay? When that happens, we have chip thickening going on the left side of the tool and chip thinning going on the right side of the tool. And of course, this is relative to the quadrant with the relationship to the direction that the tool is traveling. Several things are happening over here on this left-hand side that are very, very bad things. Number one, at the beginning of it, all the way up to the heaviest point of the chip, the thickest point of the chip, the pressure vector is actually pushing in the opposite direction of the tool travel. And so we're creating a linear or a bending force on this tool, which again, as we talked about earlier, carbide doesn't have a real good tensile strength. So a bending force or a linear force against it is not a good thing. And for years, we discovered that we can really only go about a quarter diameter to generally up around a half diameter depth of cut in a traditional pocketing before we wind up snapping the tool off. And that's because we're putting all this huge linear force against it. Notice that as the flute achieves the 90-degree quadrant area, where the chip is at its thickest, the force vector is almost virtually 90 degrees to the direction of travel, which pulls the tool off of this edge and is why we always have to come back and do a flex cut. Okay? Pretty simple physics. What we don't want is we don't want this pressure vector oscillation. So one of the things that happens right here, unfortunately, is that the effective rotational velocity, as it applies in the equation, the ratio of rotational velocity to forward velocity, suddenly becomes zero for an instant in time. When, at the exact moment that the flute passes the 90-degree quadrant right here, that effective rotational velocity is zero, but there's still forward velocity on the tool. And so therefore, the pressure vector actually flips to the outside and is in a full tangent force alignment with the flute edge. And this is what creates that harmonic vibration that we see, because immediately after the tool passes the 90-degree quadrant, that pressure vector comes back to where it belongs. Okay? And so every time the tool goes past this zone, with each spin, you get that bad vibration. Okay? We resolve that issue because we only allow the tool to go between a minimum of 10 degrees and a maximum of 80 degrees in the cutting angle. So in iMachining, it will never see this 90-degree quadrant. So therefore, there is no vector flip and there is no harmonic vibration. That's one of the things that allows us to move significantly faster and take more material in less time. Now, how does that work? Well, let's go back and look at a traditional toolpath pattern and remember what we're looking at. In a toolpath pattern from a traditional pocket, we've got all these sharp corners that create those negative influences that we're talking about. Because of that, we've never been able to go very deep of cut. And so essentially we're not using most of the tool, right? So our tooling costs go way up. For years, we did something called standard tricoidal, which basically let us orbit the tool into those zones. And it helped a little bit, but it really wasn't the right thing to do. It gained us a little bit, but it really didn't gain us a whole lot. With iMachining, we actually changed the motion of the tool. So let's follow the center line of the tool here and see what it does. As we go through here cutting, we're at cutting velocity, cutting performance feeds. Then we helix off right here. Then this is a G1 high feed rate repositioning move. Then we helix back in, and we go back into the cut. Then we helix off again, high feed rate reposition, helix back down, cut again. Helix off, high feed reposition, back in, take the next cut. Notice there is not a single sharp corner anywhere in this toolpath. Therefore, we can manage the cutting angle and maintain it within that area that is so profitable for us. Okay? Now, morphing spiral and separation channels are kind of interesting. The morphing spiral, if we can cut from the outside and morph in to the center, then we'll never run into an internal corner again. So it's much easier to manage that cutting angle and make sure that we don't over-engage, and we're keeping the tool cutting the entire time. Remember in this, as we do this, this is actually morphing spiral cut, but it's in a D-slot tricoidal mode where it's repositioning actually around half of the movement. So this is going to be far more effective if it is done right at removing material in a time frame. But in order to achieve that on an internal area, we first would have to do a separation channel to clear an area so that the tool could move around this block from the outside and work its way to the inside. So that's what this separation channel does. Now you notice a little something weird going on here. If we were to take this width of channel all the way out this edge, we'd wind up leaving a thin wall over here. Now a thin wall, because we're at depth of cut, can be a dangerous thing because you could pull that wall over into the tool if you get it too thin and cause the tool breakage. So what we've done is we created what we call a thin wall thickness parameter that allows us to have the algorithm look at that, and if this channel would violate that thin wall thickness, then the algorithm automatically expands the channel and just takes that wall out so we don't have to deal with it. Then we can come back, do the outside-inside morphing spiral here, and be done with that product really quick. Okay? Pretty big difference from this style toolpath pattern, isn't it? Now, one of the things that a lot of people will recognize here, and they do it quickly, is, yeah, but this is a whole lot less linear distance of tool movement. And that's not exactly correct. It is less, but it's not a whole lot less. This is a 1-inch deep pocket on a 1/4-inch tool. So at a 1-inch deep pocket, we're going to take about a 50 thousandths depth of cut. So we're going to have to do this pattern 20 times. That means it's a lot longer in distance than it looks like. This pattern, we're going to do at full depth of cut. Believe it or not, 1-inch depth of cut. I've actually cut very successfully, even on a 1/4-inch tool, at up to 5 times diameter depth of cut with iMachining. It's pretty amazing what it does. So this amount of distance, and we're going to travel a whole lot faster, is going to be achieved much, much quicker than this toolpath here. It's amazing how that works. But now let me talk a little bit about a morphing spiral. Morphing spiral is kind of a two-edged sword, okay? If it is done incorrectly, it is one of the most inefficient methods for material removal. If it's done correctly, you can't beat it. It is by far the most efficient material removal method available to man, okay? So let's talk about that for a minute. If we had a long, narrow area that we had to remove the material, if we just did a simple separation channel along this back side, and then we wanted the morphing algorithm to control the collapse to a center point from this edge at the same time that it controlled the collapse from this edge to the center, the only way to do that is along these long rows, we'd have to be at or very near the minimum cutting angle. Across this side, we would be at or very near the maximum cutting angle where we're getting great efficiency. But again, along the long side, we'd be at or very near the minimum cutting angle where we're getting pathetic efficiency. Okay? And so if we did that to a single collapse point, that this shape in a morphing spiral would be terribly, terribly inefficient. However, we figured that out, we looked at it, and what we did was we came up with a way for the algorithm to automatically study the topology and split this into more symmetric zones where we can then keep the tool at or very near the maximum cutting angle in the morphing spiral where we're getting fantastic efficiency. And so by doing a couple of quick separation channels here, suddenly this morph, and this morph are many, many, many times more efficient than the other single morph would have been. Okay? And so it's a way of doing that. We get these optimized spirals. So the bottom line is the system is going to look to efficiently optimize the toolpath however it can. And so even if we're doing an inside-out spiral versus an outside-in spiral, we're going to try to start with, anytime we can, a morphing spiral. If we run into obstacles where we need to clear them using the D-slot trochoidal style motion, then we're going to clear those. But if it's possible, we're going to return to the morphing spiral. Okay? We'll do what we got to do. If we got an obstacle we've got to clear it. But even if it's just for a very short time, if we can return to morphing spiral, we're going to, because morphing spiral cannot be beat for efficiency of material removal when it is done correctly. Now, at some point, in a lot of different shapes and sizes, you don't have a choice. You have to go back into what we call the final parallel passes, or the D-slot trochoidal style of motion. These are all morphing spiral cuts, okay? But they're just done in a D-slot trochoidal style, and we use detour repositionings, as I was showing you and talking about in the live cut, to move the tool more effectively back to the start of the next cut. Because these are all morphing spirals, we can actually make longer, more effective cuts than if we used a constant step over or a constant cutting angle or something of that nature. And so again, we gain efficiency with the morphing spiral, and we gain repositioning efficiency with the detour repositions and the regionalized optimization. So it becomes a very, very quick way to remove the material. Two final things. Go ahead.
Yeah, I got to chime in. This is all done in the software, so it's literally like having a 30, 40, 50-year experienced machinist.
Oh, it's fantastic.
Taking care of it for
fantastic.
You,
and just a quick anecdote, or whatever you want to call it. I was speaking with a gentleman the other day who, I won't say the competition's name, but their product that they claim does this, or does something similar to this. They had to write 21 tool paths in order to achieve the cut. It took them 2.5 days to program the part. Our software did it in a single tool path that took me about 20 minutes to program. So it's just a huge, huge difference. And our cycle time was faster. So it's an interesting concept when you really dig into the details of what's going on in these systems. And there's a lot of Me Too's out there that are claiming that they're as efficient as iMachining. But when you get into the details, we have 7 patent claims against our software that nobody else can touch. Okay. We do rest machining. So if you want to move this with a bigger tool out here and then come back, pick up these spots with a smaller tool, you can. We also do something we call iFinish. iFinish is rather interesting. Believe it or not, if this model radius is very near the tool radius, even if I'm only leaving 10 thousandths wall stock in here for the finish, when I come back through here and do a single cut through here with the finish, I can wind up chattering these corners. You guys have all seen it. You've heard the chirping when it goes into the corner and you see the diagonal lines that it leaves, and sometimes it kind of keyholes the corner, overcuts it a little bit. Well, what's going on there is when it comes into that corner, even though there's just a tiny amount of stock on it, if it over-engages, remember we talked about that linear force pushing the tool away? Well, that happens, but unfortunately there's only 10 thousandths of stock, or whatever you've left. If it pushes it away far enough that the flute actually comes out of the cut, then all that force goes away. That tool springs back into the part, winds up overspringing and causing that keyhole cut, and then re-engages the force and pushes it back out again. And that's what causes that chirping and chattering, because it does that on each flute that rotates through there. And so if you'll notice, if you ever see that corner chatter, look at the diagonal lines. They will identically match the helical angle of the tool. That's where the flute is coming out of the cut. Okay? So iMachining goes in, automatically calculates where those over-engagements would be, and it clears them out down to the minimum cutting angle so that it can come through with a final contiguous cut and cut it nice and smooth without any kind of chatter or chopping. Okay? Well, that concludes it. Thank you guys for sticking around. I appreciate it. I hope that was helpful for you. If you have, again, any interest in seeing a little bit more, please connect with Steve, and we'll get you set up for a full-on demo of the software and see if it's something you'd be interested in.
Perfect. And thanks, Ken, for that good presentation. Appreciate that.
Oh, you're more than welcome. Thank you, Andres and Ricardo, for doing the cut for us. What a great machine you guys have built. If you guys have any questions about the machine, again, get in touch with Steve. Steve can connect you up with the guys over at Levil. And I think you'd be very, very impressed with their machine. It's real nice.
All right. Well, with that, we will wrap it up. Thank everybody for the time one more time, and have a good rest of your day.
All right. Thank you, everybody.